All right, we are ready to start talking about processes. So this is the first kind of concrete thing that we want to explore in operating systems. And the way to get this started, I think, is to just write a really simple Hello World program. All right, so I'm going to write that. So pound include IOStream using namespace std, and then just a real short program, int main void, and then cout. Hello world. And that's it. That's all I'm going to do. All right. So this is a really super short program. I guess we'll do a return -1 or return 1. It's a really short program. Now, you are at the point where this program probably makes a lot more sense than it did just a week or two ago when you were watching lectures about C++, but you weren't actually writing C++. But now you've submitted a homework assignment or close to that is a fairly, a reasonable sized, medium-sized C++ program. So I just want to walk you through the process that gets followed as we take the C++ program. And first, what we're going to do is we're going to compile it. And when we compile it, we're going to end up with, if this is main.cpp, when we compile it, we're going to end up with a program that is main.o. All right, and this is called an object file. If you looked at the code in an object file, it looks a lot like machine language instructions, or very close to machine language instructions. Not quite, but close to instructions that would be things that a microprocessor could execute in order to run a program. So it's gone from C++ to a very low level language. Okay, now that is not the program. Main.o is not the program. What we need is an executable. And so to create the executable, we go through another process called the link process. So the link process creates main. And main is an executable program. All right, but it's still not the program running yet. So main is a program that's sitting out on the disk. Now, if we want to run it, we would say, I'll just continue this process. If we want to run it, at least in Linux, we would say /main, saying, look at my local directory for the program main, and please run it. And so what happens is that at this point, the program, the executable program main, gets loaded into the computer's memory. And gets run. So now this is a running program or a process. And we can run main multiple times if we want to. So I did /main once, but in Linux, you can run things multiple times. So if I do /main on the command line and do an ampersand right after it, it will take that main and load it into the computer's memory and immediately return with a command prompt. And I can say /main again and run it a second time, this time without the ampersand. Just want to make sure you guys are clear on that this is an ampersand. So I can run it without the ampersand the second time, and then the program will, the command line will wait for the program to run. And we're running main again, and this is another process that's running. So what I'm trying to show here is that from a single main executable up here, we can end up with multiple main processes running here in the computer's memory. All right, so what is a process then, since that's what the topic is? Well, in operating systems, what we say is that a process is, whoops, that'll be hard to read. A process is a program in execution. All right. So that's why I was making the distinction here between the main over here, which is the executable. So it's the program, but it's not being executed at that point. It's sitting on the disk. And this command, /main, which is then taking the executable on disk and saying, load that executable into the computer's memory and start running it, operating system. Okay, so let's talk a little bit about, I'm going to switch gears here and write some notes using the editor. Just looking through my notes. The next kind of things that I'd be writing are sort of texty. So I feel like I can stop with the, I don't have any pictures to draw right now. So I think I'm going to jump over to here. And let's say Emacs, why don't we call this process class notes. Oh, I used lowercase, so process class notes. Okay. All right, so let's talk about processes. So definition, a program in execution. Okay. All right, so let's talk about process creation. How do we do it? And I'm gonna just put this up here too for you. All right, cool. All right, so process creation, how do we do it? Well, what events cause processes to be created? What kind of events cause processes to be created? So why don't you think about this for a second? What are the things that could trigger the creation of a process? All right, so we just had an example of that. So there's one category there, but there's some other reasons why a process might get created. So one is a user request to run a program, okay? So that might be clicking on something, on your desktop, or it might be touching an app on your phone. It could also be, if we're dealing with Linux or using the terminal window in OS 10 or the command prompt in Windows, it could be just the user typing a command in from that command prompt. All right, so a user request to run a program. Another way that events can be, processes can be created is this at system initialization time. So when you turn on the computer, a whole bunch of processes get started when you turn on the computer. I can show you just as an example. Actually, what I'll do is, this is kind of cool. You can pause a process. So like Emacs right now is running. It's a process that's running. What I'm going to do is I just want to show you all of the process, not all of them, but actually, yeah, what the heck, we might do all of them. All the processes that are running right now on my Linux virtual machine. And pretty much all of them got started because I told the Amazon Web Services to boot up the virtual machine and start just booted up, and I haven't done really anything other than booting up the machine. So I'm going to hit Control and Z. When you hit Control Z, what it does is it takes the process that's currently executing, that's accepting keyboard input, and it pauses it. Okay, it stops the process. So if I hit FG, boom, I'm back in Emacs again. If I hit Control Z, boom, I've stopped Emacs. It's still running. I just have paused it. And I just wanted to get back to the command line to do something here to show you. So if I type PS minus EF, that says, hey, Linux, why don't you list all of the processes that are currently running? So, whoa, a lot of them just scroll by here. But look at all that stuff. Holy moly. So almost all of these processes are running and were started at the time the computer booted up. All right, at the time the virtual machine booted up. I'm just looking to see if there's anything. There's my Emacs command. There's the process ps minus ef, the command that I just typed in. Bash, that's the command prompt right here that's accepting the input from me as I type in commands to create new processes. There's a lot of other stuff here, some of which I don't know. I'm just looking to see if there's any other juicy ones. Well, there's I'll do ps minus ef grep tty. So these processes are ones that provide a terminal support for the terminal window that I'm interacting with. So and this one, SSHD, is providing support for the connection that I made from OS 10 into the virtual machine. So there's a ton of processes here. Some of them are owned by root, that's the administrator. Some of them are owned by Ubuntu, that's me, I'm the user, Ubuntu. Whoopsie, I have no idea what that is. Kind of cool name. So anyway, lots of processes running. Most of the ones that we're looking at here were started at the time that the computer was initialized. All right, let's foreground this again. That's system initialization time. The other way that a process can get started is another process, requests. Okay, so what that means is that a program can be running, and the program itself, the process that is running, the process itself can request that a new process get created. So that's pretty crazy. But if you think about it, another process request allowing new processes to be created really supports both system initialization time and user requests to run a program. So if a process is allowed to ask for a new process to be created, then the shell, like the bash shell that's reading in commands, as I type different commands, can read in a command to do something, create a new process, and then execute that command as a new process. System initialization time, as the system boots up, the process of bringing an operating system online with all the support that it needs can start with some really primitive processes. Those are called the kernel processes, and those kernel processes can spawn other processes to make the operating system useful to regular users. All right, I want to talk a little bit about system initialization. Initialization. I'm having trouble spelling here. All right. There we go. There. That looks better. I hope I spelled that right. It's hard to see when you're at the elemental lecture and you're typing, you're going, did I spell that right? I think that looks reasonable. Okay. So at system initialization time, I wanted to talk to you a little bit about the process that is typically followed by a Windows machine, OS 10 machine, Linux machine. There's a lot of there's a process that gets followed. So I want to talk about that process. So um, the process is also called booting, and I want to, and you may have used that. Oh, I'm booting up my computer, right? Or I'm booting up the virtual machine. So why is it called booting? Well, it's called booting because we're pulling the system up by its bootstrap. So that's a saying. You're getting pulled up uh, by your bootstraps. So it's kind of a basic operation of the system kind of coming to life. So what is this thing called the bootstrap? Well, when you turn on your computer, most computers do something called, well, let's follow this process. So we're going to turn on the computer. The computer performs something called a post. So the post is power on self test. It just looks to make sure that all of the devices are working properly. All right, so you don't have any hardware errors. It can find the hard drive, it can find the keyboard, it can find the screen. Okay. Then what happens is we initialize memory, registers, and controller. Now, one thing, I just have a note here. How does the computer know to do this power on self-test? Via BIOS. So there's a small program in the computer, in any kind of PC or PC derivative that is a real basic input-output operating system. And it's just a small set of commands that gets run that does this power on self-test, and then initializes memory, register, and controller. So the controllers allow the CPU to talk to various hardware devices that are attached to the computer. And then via BIOS, we run the bootstrap. So the bootstrap is a program or a process that loads the operating system into memory. So it has to figure out where the operating system is first. So here is the bootstrap. So search devices in some order. So I said devices, but it's really search IO devices. So we're going to search IO devices in some order. So the order could be, maybe we're searching USB first, then the network. Actually, the order would probably be like this. USB, probably be this. Hard drive, USB, and then maybe network. You can control by editing, by booting the computer up and going to the BIOS section of the computer. And this is something that most computers have there's like a function key that you press or a series of keys that you press and hold down after you turn on the computer. And if you F2, for example, or F10, so you just turn on the computer and you hold that key down. And what that tells the computer is like, hey, don't go through the regular system initialization, jump right into the BIOS configuration. So if you've never done it, it's kind of cool. So you hold this key down, turn the computer on, it dumps you into BIOS, and one of the things, BIOS lets you fiddle around with a lot of different things, but one of the things you can fiddle around with is the order that IO devices are searched in order to do this bootstrapping process, all right? So in other words, it's the order that the IO devices are searched to find the operating system that's going to be loaded into the computer. So if you change the order, you can influence which operating system runs on your computer. So for example, if the hard drives first search first, then USB, then network, if you go into the BIOS and say, no, search the USB first before you search the hard drive, then if you have a USB with a decent amount of memory on it, you could have Linux, for example, installed on a USB stick, or Windows, or actually probably not OS X, but certainly Linux or Windows. If that's plugged into your computer and BIOS searches that first, then instead of booting up whatever the operating system is that your computer normally boots up with, you can boot up with, for example, Linux. Pretty cool. Okay, so typically then, once it's located the I/O device, it's going to look at cylinder 0, track 0, sector 0. So this is an address on the I/O device. So the I/O devices are often, in many operating systems, these I/O devices, the hard drive, the USB, and even the network to some extent, present themselves as if they're a large hard drive or a large disk drive. And the cylinder 0, track 0, sector 0 is an addressing scheme that says go to the first cylinder on the hard drive. So that's like, it's like maybe not cylinder, I might say, I don't know. Yeah, we'll call it cylinder. So the cylinder is a location on the hard drive that hard drives prior to the solid state hard drives were comprised of platters or a series of disks, and you could target a particular disk surface to start reading from. So that cylinder 0 is targeting a particular disk surface. Track 0 is a location on that disk surface, a ring on the disk surface, and sector 0 is a slice of that ring on the surface. So typically the bootstrap starts at the first location, the first address on the disk. Okay, so we're going to load the OS program, which is called the kernel. And we're going to execute, and then we're going to execute it. As a process. All right. In Linux, this process is called init. And then what is going to happen is that init is going to follow some configuration files, and it's going to look at other processes. And I have some notes here. So I just want to be clear here. So I'm saying execute this as a process. This in Linux, this is called init. And then from init, we are, and other operating systems will do this as well, there's a configuration file, typically one or more of them, that has a list of other processes that init should start up, other programs that init should start up and load as processes to get the operating system put together for users to use it. So for Linux, we're going to consult a init.d configuration file. After init. Okay. So these special processes that are run after init, but before a user would actually start running programs. So in Linux, these are called, still doing bootstrapping here. Linux calls these daemons. I guess I should say Linux. there. So Linux calls these processes past the kernel, but that are loaded by this configuration file, calls them daemons. And Windows calls them services. I don't know what OS X calls them. I mean, OS X grew out of Unix, and Linux and Unix are related, so I suspect they're probably also called daemons. Okay, cool. All right, so that takes care of system initialization. We kind of went down a rabbit hole with that, but it is kind of cool. I mean, if you were curious about what BIOS was and why you may have read that there are different ways to boot up operating systems on your computer and how that all works. Now you know a little bit about that and why it's called booting up your computer. Okay, so we talked a bit about a user request to run a program. We talked about system initialization. I haven't talked in detail about how a process A could request that process B be run, and I would like to spend some time talking about that. So I think to do that, it would be worthwhile actually to write a program. All right, so this is the first program that would kind of demos how to, I'll save this, and we'll create a program that's called, we'll call this fork, or process. I think we'll just call it fork. No, we'll create a directory. Okay, yeah, okay. Let's do that. All right, so make sure I didn't, yeah, okay, good. It's saved. So I'm gonna make dir, I'm gonna make a process fork. All right, and I'm in that directory. I'll just copy the stuff from, we'll copy it from hello world because I don't really need anything fancy. And I'll get rid of that C++ thing. Okay. Okay, so here's my little hello world program. So what I like to do is I'd like to demonstrate to you how one process, this main program, can start up another process. It's pretty cool, all right? So the way we're gonna do this is I've got my main program and I'm gonna create a variable called PID. So PID is the process ID. And I'm also going to create a local variable called, well, okay, let's, yeah, we're going to do this in two phases. So phase one, we're just going to demonstrate basically how to do the process creation. Then we'll do some investigation after that. I think that's a good idea. All right, so there's PID, the process ID. All right, so what we're going to do here is we're going to say PID is equal to fork, F-O-R-K. So what fork does is it's a special system call to the operating system that says, hey, this process that's running right now would like to start another process, please. All right, so fork is really cool. It will return one of the following. It's going to return 0, or non-zero. And this is where things get kind of funky. If the PID is 0, it means that the process that's currently running was created by the main program. So I know that's crazy, but at the moment we call fork, what actually happens is a second process comes into existence and it's running exactly the same code as you see here. And both processes return from fork. and begin executing right here. Right here. Okay, so we say PID equals fork, and immediately a new process comes into existence, and now both processes go to the next line of code to execute. Now I'm putting right here, it's a comment, so it's really not going to execute that line, but it will execute the next line, which is this. If, okay, so we'll do this. I'll get rid of the right here now. I'll say if PID is less than 0, then there was an error. Okay, and so I'm going to say C error. That's like C out, main colon, fork failed. And I'm going to do exit. I'll say, I can just say return -1. All right. If the PID is else if PID is equal to 0, then what happened is, remember, if the fork is successful, the PID will either be 0 or non-zero. I guess I would say the PID is 0, greater than 0, or less than 0. If the PID is less than 0, it's an error. If something bad happened. This actually can happen. It's happened to me before when I've written a program, and this may happen to you, when I've written a program that creates too many processes. There's a limit to how many processes the operating system can handle, because processes are resource intensive. So once you exceed that limit, fork will fail. So you can start getting PIDs that are negative, and if that happens, you just have to stop your program. All right, so after the fork returns, we have two processes running. The original process, the sort of, we're going to call it the parent process, and the child process. So I think actually we'll deal with the parent process first. We'll do the child process first. Let's do the parent process, because you're used to. I keep changing around. Let's do the child process first. Okay. So I'm just put a little comment here and say that's an error. This is the child process. And if we're the child process, we're going to say, we're going to do the following. We're going to do exec LP let's do this. That's too complicated. Let's just do C out. I am the child process. Okay. And else. Okay, if the PID is not negative and it's not 0, then we are the parent process. So we're going to say else I am the parent. Okay. So I just want to take a look at this for a second and see if this makes sense to you. All right. So what we have here is this really interesting method call called fork. It's a system call into the operating system that says, yo, operating system, at this point, I would like to start a new program running. So the operating system handles that request by saying, no problem, I will give you a new program, it will start running. Now at this point, there's not one process running, there are now two processes running. a parent process and a child process. They both immediately return from fork, and now there are two processes running. They both check if PID is less than 0. Hopefully, it will be less than 0. They both then check else if PID is equal to 0. Now, if the process is the child process, it will have a PID equal to 0. That's how the child process knows it's the child process. Fork returns for the child process with a PID of 0. So the child process then says, I am the child process, just like that, in that kind of voice. All right, and then it exits this else if and does a return 1, and then it's done. It stops running. The operating system says, okay, child process, you're done running. At the same exact time as the child process is checking if PID is equal to 0, the parent process is also checking to see if PID is equal to 0. And for the parent process, the way the parent process knows it's the parent process is this PID is not 0. In fact, this PID is the ID of the child process. So that's kind of cool. It gives the parent process some information about the child process that got spawned. And so the parent process will not satisfy this else if PID is equal to 0, and will skip onto this else statement, and then it will say, I am the parent process. And then it too will return an end. So at the same time, we have the child process printing, I am the child process. The parent process will also be printing, I am the parent process. All right? That is wild. So you've never had code, I suspect, that you've ever written so far as a programmer that allows two things to run at the same time. All right, and so I just described how that can happen. Two separate processes running, fork returns from its call, and now we have two separate processes at the same time running, and they're both checking if PID is less than 0. They're both checking if PID is equal to 0. One of them, it satisfies and prints I am the child process. The other doesn't satisfy, so it goes to the else and prints I am the parent process. But this is all happening at the same time. Wild, really wild. Okay, well, I know in order to use fork that there's something I have to include, but I don't know what it is. So I'm going to say man fork. Man page, how do we do forks? Okay, so it looks like we have to include these two include statements in our program. So I'm just going to go up to the top here and add those two right up at the top. All right. And I'm going to make. Okay, I don't think there's anything running. So I just made the program. And so what I want to do next is I want to run it. So I'm going to do /main. Now, I want you to understand, when I say /main, what is going to happen is the main program is going to be loaded into the computer's memory, and it now becomes a process. This is the parent process, okay? And then when that fork command gets executed, the parent process is going to spawn off a child process. The child process is going to say, I am the child process. And the main process, the parent program, sorry, the parent process is going to say, I am the parent process. So let's watch this. Okay, that's kind of cool. So it looked like the main process got a chance to say, I am the parent process, before the child process got to say, I am the child process. So, but there were two programs running at the same time. That's very important to understand. Let's try running it again. Let's try running it again. So if I put a little bit of a delay in the program, I'll just do that. Maybe we can get the child process to run first before the parent process does. Let's do this, just so you can understand that there's two programs running at the same time. You may not be believing it. I mean, part of it, I would think the proof would be, look, this if statement is set up, there's only one of these if conditions that will be satisfied. So there's no way that a single program running can both print I am the child process and I am the parent process. That's not possible. But just as an added thing, let's do this. So I'm saying enter a number, please, and I'm going to say int num, and I'm just doing this to slow the parent process down. Just so you can see that right now, it's the parent process always wins when we run this, and the child process gets to print I'm the child process last, but now I've slowed things down. And so when we run main, watch what happens. Do you see what just happened? It says enter a number, please. And then somebody said, I am the child process. So the child process wrote out, I am the child process. The main process is still waiting. The parent process is still waiting for me to enter a number. So I enter 1 and it says, I am the parent process. Pretty wild, right? So I'm trying to think of what else I want to show you here that's sort of interesting. Well, okay, I've got a bunch of cool things to show you here. So let's take a look at them. So the first thing I like to do is I like to flip this so that the parent process, so that the child process accepts the number, not the parent process. So it says, I am the child process. And in fact, to make it really clear, I'm going to say child says this, and the child says this, and the parent says this. But I'd like the parent to wait. I want the parent to wait until the child is done executing. So you can actually do that. And the way you can do that is you can tell the parent, look, let the child process run. When the child process is done running, then you can continue. So the parent process is going to fork. The child process is going to go off and do some stuff. In this case, say, I am the child process, and allow a number to be entered. Then when that child process is done executing, the parent process will continue. So how do we do that? Well, the way we can do that is we can coordinate between the parent process and the child process by using a method called waitPID. So what waitPID will do is tell the process that executes waitPID to wait until this PID returns, this PID is done executing. Sorry, this process is done executing. All right, and in waitPID expects an argument, PID, which is the process ID. So if you remember, if we go up here to look at fork, what I told you about fork is that when the fork happens, the PID of the process will get set. If the PID is 0, we are the child process. If the PID is non-zero, then we are the parent process, and the PID value is the PID of the child. So down here, if I say waitPID and I pass in the PID, this PID is the PID of the child. For the parent process, we get to know the child's PID. Okay, and then we're going to pass in something called status, which will get set, and then 0. And I think status is an int, but I'm not sure, so I'm just going to go out to the man page and say man waitPID. So waitPID takes an integer. Okay. All right. At least the version I'm using. So let's, oops. There we go. Get a little confused there. Okay. So we'll create a local variable called status. We'll set it equal to 0. And now we're going to call waitPID. We're going to wait on the child process ID, pass in a reference to an integer, and then we're just going to pass in the value 0. That means just block until the child returns. The child exits. The child process stops running. Okay, so let's make this. Oops. Looks like I might have to include something else. Oh yeah, looks like I have to include syswait.h. Okay. All right. All right. All right, so notice, I want you to observe what happened here. So the child says, I am the child process. And the child says, enter a number, please. Also, I want you to notice that the parent is not saying anything right now. And that's because we told the parent, wait until the child is done running, then you can run. All right, so the parent process is running right now, but it's hanging out and waiting. It's delaying, it's paused, waiting for the child process to finish executing. So we'll enter a number, 42, press enter, and now the parent says, I am the parent process. All right, so let's just go look at that program one more time, just so you're clear on what's happening. So we do the fork, the child process is allowed to run. It says, I'm the child process, and waits for the user to enter a number. Meanwhile, the parent process is hanging out, and it's hanging out using this wait PID system call. So it's telling the operating system, yo, operating system, I'm going to wait. I don't want to run until my child, identified by PID, this process ID, is done running. And as soon as the child's done running, the parent then says, I am the parent process. Pretty cool. Okay, so let's try something here. All right, let's try something interesting to see what you would expect to see as output if I do the following. Let's create a variable here. We'll call it int the int. And we're going to set the int equal to 42. All right? All right. Now, here we are in the child process, and the child says, enter a number, please. And we read that number in. And then what we're going to do is we're going to set the int equal to num. All right, so all we're doing is the int originally has the value of 42. Now we're saying the int is equal to num. So whatever gets entered here when the child process is running, the int is going to be reset to. And then down here, after we come back from the wait PID, the parent says, I am the parent process. Oh, let's do this. One more thing just before the child finishes. We'll say cout child. The int is the int. Okay. And then what we're going to do down here is we're going to have the parent say, parent, the int is the int. All right. So the child process is going to change the integer, then exit. The parent process is going to wait for the child process to finish, and then print out I'm the parent, but then also print out the value of the int. So the question I have for you is, what is this value going to be? And what is this value going to be? Okay? So the int changes in the child. Does it change in the parent? So the int changes in the child. Does it change in the parent? Interesting question. So that will help you
understand the model of what a process is like when it's running in an operating system, okay? We have two separate independent processes that are running, the child process and the parent process. So the child changes the int. Does it change it in the parent? What do you think? Well, let's try an experiment. All right, I am the child process. Enter a number, please. Okay, so right now the int has the value 42. So we'll enter a number of 100 and press enter. What do you think is going to happen? What will the child say? What will the parent say? Well, the child said the int is 100. So in the child's process memory, the int got changed to 100. But in the parent's process memory, the int remained 42. Even though both the parent and the child have access to that int in the same way, the int is a local variable created on the stack for the main program. But you see there's two separate processes. So that means there's two separate main programs, and that means there's two separate ints. One int belongs to the parent process, the other int belongs to the child process. The point at which the child process gets its information about the int and what the values are for the int is right here when the fork happens. So at the moment the fork happens, when that fork happens, the entire memory space for the parent program's process gets copied over into the child process. And then at that point, the two processes begin to execute independently of each other. And any change that the parent process makes to its memory is not visible to the child process. And any change the child process makes to its memory is not visible to the parent process because they have their own independent process and memory space. All right. So I have a diagram that might be able to help, or I'll draw a diagram, I guess, that might be able to help reinforce this idea. All right, I have to find my magic pen. There it is. Okay. So here is our parent process. So the parent process has a bunch of different pieces in it, okay? So the memory space for the parent process looks like this. We've got a stack. This is where local variables are associated with the methods as they get executed. And the stack is growing down, and we have the heap. The heap is growing up. All right. So when you do a new, you're going to be allocating chunks of memory on the heap. When you create a local variable like the int, which is equal to 42, or PID, these are created on the stack. All right, there's also a chunk of memory called static data. So if you create a global variable, the process space memory associated with a global variable is located in static data. All right. There's also a section of memory that's called the code or text segment. Generally, the code or text segment is read-only. The static data is read-write. So static data doesn't grow or shrink. It's fixed at the time that the process is loaded in memory. So if you have a lot of global variables declared in your program, so these are variables that are declared outside of any method, those variables are going to be allocated to static data. So the advantage of the stack and heap is it can grow and shrink as your program needs it. The advantage of static data is that it's fixed at the time the process is loaded, or the program's loaded into memory and the process starts executing. It doesn't grow or shrink. So that's not a great thing, because if you have a lot of global variables, your program can be kind of bloated because the static data will never disappear. But the nice thing is there's no time associated with allocating the memory associated with the static data once the process starts running, because it's the data is always there. Okay, so that's the parent. Now, at the moment that we do the fork, what happens is a complete copy of the parent gets made for the child. So the moment we do the fork, right, when that fork gets executed in the main program, we create a complete copy of the parent and start executing it as a separate process. This is the child. So we're making a complete copy of the parent's memory space. So at that point, anything that's on the parent stack is also on the child stack. Anything that's on the parent's heap is on the child's heap. Any global variables that the parent has, the child has those as well. But these are two completely separate chunks of memory, the parent's memory and the child's memory. So as the child begins to run, and by the way, let's say the PID is equal to, for the parent, the PID will be the PID of the child. So let's say the parent's PID, the parent's process ID is 4369, okay? So if you were to say, hey, operating system, what's the PID of the parent? It would say 4369. Let's say the child's PID is, process ID is 4370, okay? Now, at the moment the fork occurs, the PID for the PID value, the local variable PID, that's or to put it a different way, fork returns the PID of the child to the parent. The PID of the child is going to be 4370. All right. Now, the child fork returns a PID of 0. That indicates, hey, you're the child. Okay. All right. Now already you can see that it's possible for both the parent and the child to have different PID values. And that's because they both have their own independent stacks. All right. Now, a little bit later, the child sets the int, changes the int from 42 to 100, and then prints it out. When that change gets made, the parent's int doesn't get changed. The parent has its own int on its own stack. So that int remains 42. And that's how both the parent and the child can execute, can have the same local variables and change those local variables, but they don't interfere with each other because they're running as two separate processes with two separate chunks of memory. Okay,